This is Jose Roca, and I will present the work entitled Flow of an Elastic Microcapsule Through a Constricted Channel. It was made possible by the LNP Lab with the support of Professor Marcio Carvalho and Professor Ivan Meneses. Flow of suspended capsules can be found in different applications, from red blood cells to suspension of capsules in porous media. For instance, red blood cells flow in biological systems have received a lot of attention over the years. We can find different numerical and experimental analyses of finding what parameters affect the flow of suspended capsules. In this work, however, we will focus on porous media applications. The lab has developed some studies in such regard, using suspension of microcapsules as a method to enhance the oil recovery by reducing water mobility, blocking perforation flow paths, and diverting water to oil-containing pores in the process. In order to understand the dynamics at the microscale level, a constricted channel can be used as a model of a bore throat connected to adjacent core bodies. Suspended capsule flow is a challenging problem because we need to take into account the complex interaction between fluid and solid phases. In general, this problem depends on different parameters, including the surface capillary number, defined as the ratio of viscous to elastic forces. In order to solve this problem, we need to consider that for the fluid phase, mass and momentum equations for an incompressible Newtonian fluid requires to be solved. For the solids phase, on the other hand, membrane dynamics is governed by equilibrium tension on the membrane. We consider that the membrane material follows Hooke's law. With the appropriate boundary and initial conditions and the coupling between fluid and solid phases, we solve a numerical problem using finite element with immersed boundary methods. Two different grids are used: quadrilateral elements for the fluid grid, which is fixed, and 1D linear segments for the solid grid, which moves and deforms as time evolves. As we can see, the capsule moves to the constriction and gets deformed. Notice how pressure difference between inlet and outlet behaves in time, reaching its maximum when the capsule is at the constriction. Pressure peak is of paramount importance to our study. We can run different simulations for different surface capillary number. The lower the surface capillary number, the stiffer the capsule, the higher the pressure peak. Running for other parameters as capsule radius and pre-stress conditions, we found different curves. The blocking mechanism is only effective if local surface capillary number is low enough. I would like to thank this institution. Thanks for watching.